Now, I'm going to give you just an overview about the etiology of algorithms. So what is the origin of the word algorithm? So the word algorithm, just a brief overview. It started with this scientist. His name is Muhammad ibn Musa Al-Khawarizmi. So he is like a mathematician. Right? Yeah, you guys can see. I can speak Arabic. But no Turkish. I'm still learning Turkish. Doing my best. Okay, great. So here, algorithmy comes from the name Al-Khawarizmi. So he's a Persian mathematician, astronomer, geographer, Islamic scholar in the House of Wisdom in Baghdad. And you can see how people in the old time, they used to do so many things and be experts in different fields. I wonder why now we're not like that anymore.
Because everything is so detailed.
Everything is so detailed. You can find people now specialized just in studying, like not just the brain, but neurons, like just, the microscopic world of the brain. So, or maybe, just the kidney. So, like, you can find a person spending their whole life to understand how the kidney works. Great. So, here in 825, he wrote a treatise in Arabic translated in the 12th century to Latin. So, when it got translated, they called it algorithmy. Okay, so it's the translation of his book, and that's how the word algorithm was generated or has originated. Okay, now actually, this is in terms of the name algorithm, but the oldest algorithm dated way back before Al-Khawarizmi. It was, well, maybe there are smarter algorithms before Euclidean time, 300 BC, but this is the oldest one in the record, the history of algorithms. So way before computers, Euclid has created what we call the first algorithm. And I think all of you guys know this algorithm. It's the algorithm which computes the greatest common divisor of two numbers m and n. Okay, so you guys maybe remember. I hope you remember this. So these are you can see that this is the algorithm. So different ways of writing a pseudocode or the same algorithm. So what we want basically, if we have if n, so here we want to find the common divisor of these two numbers. If n is equal to 0, so then we can just return m. Otherwise, we proceed to step 2. So what is step 2? Step 2 here is we divide m by n and assign the value of the remainder to r. Then assign the value of m to n and the value of r to n. So you can see here it's just, this is assignments, but it's spelled out. It's written in plain English. And then we just repeat again. So we just continue to divide and take the remainder. Okay, so this is the algorithm right here. You guys can run it manually at home when you go over your notes, and you can even code it up in your favorite programming language. Now let's find the GCD of these two divisors. For example, 54 and 24. So what are the common divisors of these two numbers? So let's find them together. So we have the common divisors are 1, okay, 2, 3, then we have 6, and that's it, right? So 1, 2, 3, and 6. What is the GCD, the greatest common divisor of these two numbers? 6, okay? So this is the first algorithm, basically, okay? And you guys can look at this. So the algorithm here, you can think about it as a function. So you give the function two numbers, right? And it gives you the greatest common divisor. So you can think about it as a function. You give it an input and it maps it, it gives you an output. But later on, Alan Turing, he revolutionized the way we look at computer science and the way we look at algorithm. So the formalization of the concept of an algorithm and computation was revolutionized with the concept of what we call the Turing machine. And the Turing machine was invented by Alan Turing in the 90s. So he is an English, also mathematician, logician, cryptanalysis, computer scientist, and he had a significant role in creation of modern computer science. Okay, so what is the key idea? So what is the Turing machine is about? So the Turing machine, it's a state machine, okay? It has, at a specific time t, we have what we call a read-write head. So this is the read-write head, and it's reading numbers in this tape. So we have a tape, an infinite memory tape, and the device, it's just moving either to the right or the left, depending on the number that it has read before and what's currently reading, and some instructions, some set of instructions that are predefined. So here, so basically, Turing machine has a read-write head that can move right or left. The action of the Turing machine is determined completely by, first, the current state of the machine. So this is the current state. Okay, what's inside the moving CPU, or like the read-write head. The symbol in this cell being scanned. So this is the current symbol, okay, that's being scanned right here. And a table of transition rules that we call a for tuple or program. So given a current state S0 and the symbol that is reading, so given the current state, the symbol and an action, a given action, it will move either right or left or read or write. So it will perform a specific action that you want. So this is actually how a program works. So here, the action can be right in the current cell or move left or right. So these are the two actions that a Turing machine can take, okay? Either moving right or left, or writing in the current cell. So if it's gonna move right or left, it can read, or it can also write. It depends on the next action. So it's quite interesting that it has been proven that any computer science program is Turing computable. So which means a function is Turing computable if there exists a set of instructions that will result in computing the function regardless of the amount of time it takes, okay? And here, although the device looks primitive, so you can see that this is quite simple, right? So any program that is related to computers, anything is Turing computable, okay? It can be formalized using this tuple, this tuple of inputs, outputs, and actions. Great.